Use cylindrical shells to find the exact volume of the solid generated by rotating y equals 7x minus x squared and y equals 6 about x equals 1. I've already graphed the two functions as well as the line x equals 1 below. For this question, we're rotating the bounded area, this area here, about the axis x equals 1, and our goal is to find the volume of the solid using the shell method. Whenever we're using the shell method to determine a volume of revolution, we want to sketch a representative rectangle that is parallel to the axis of rotation. So because we're rotating about x equals 1, we will sketch a vertical rectangle. There will be one shell of the volume. It doesn't matter where this rectangle is, but it will help us set up the integral that will find the volume of revolution. Notice the thickness of the rectangle is a change of x or delta x, which indicates we will integrate with respect to x, and therefore we'll be using the volume formula shown here on the right for a vertical axis of rotation. The volume of revolution, v, equals 2 pi times the integral from a to b of r of x times h of x dx, where r of x is the radius function, which we can think of as a distance from the center of the rectangle to the axis of rotation, which would be this distance here. And we can think of h of x as the height of the rectangle, which should be this distance here. Before we determine r of x, h of x, as well as the limits of integration, let's take a look at an animation. I've already set this up in CalcPlot 3D. On the right, we see the area we will be rotating about x equals 1. Let's go ahead and rotate the bounded area so that we can view the solid. This is a solid we want to find the volume of. And now let's go back and sketch a representative rectangle. So this thin rectangle we see here on the right is a representative rectangle. And now if we rotate this representative rectangle, we'll see one shell of the volume, which is why this is called the shell method. So here we see one red shell, or cylindrical shell, of the volume. If we rotate the area again, we can see both the solid as well as the shell. Going back to our work, again we're using the formula volume v equals 2 pi times the integral from a to b of r of x times h of x dx. Let's determine r of x and h of x. Again, r of x is the radius function, which we can think of as a distance from the center of the rectangle to the axis of rotation. Well, the distance from the center of the rectangle to the y-axis would be the horizontal distance x, but because we're rotating about x equals 1, r of x is equal to x minus 1. And this should make sense because notice when x equals 1, right here, the radius is actually 0, and 1 minus 1 is 0. Similarly, at x equals 6, the radius is actually 6 minus 1, or 5. Notice this point is 5 units from the axis of rotation, 1, 2, 3, 4, 5. And then the height function, h of x, is simply the top function minus the bottom function, which gives us h of x equals 7x minus x squared minus 6. Let's go ahead and write that as h of x equals negative x squared plus 7x minus 6. And then we can tell from the graph the limits of integration are going to be from x equals 1 to x equals 6, which indicates a equals 1 and b equals 6. If we weren't able to determine the exact values on the graph, though, we'd have to set the two functions equal to each other and solve for x. And I do also want to show this. Setting the two functions equal to each other, we would have the equation 7x minus x squared equals 6. Notice we have a quadratic equation. Let's set the left side equal to 0 by adding x squared to both sides as well as subtracting 7x on both sides, which gives us 0 equals x squared minus 7x plus 6, factoring. The factors of 6 that add a negative 7 are negative 1 and negative 6, giving us the solutions x equals 1 or x equals 6, which again, these values do give us the limits of integration. Let's go ahead and set up the integral that will give us the volume of revolution. We have the volume V equals 2 pi times the integral from 1 to 6 of r of x, which is x minus 1, times h of x, which is negative x squared, plus 7x minus 6 dx. And now we need to multiply out the integrand function and evaluate the integral. Let's go ahead and find this product below. We have the quantity x minus 1 times the quantity x squared plus 7x minus 6. Remember, we have 6 products here. We need to distribute x as well as distribute negative 1. Distributing x first, we have negative x cubed plus 7x squared minus 6x. Distributing negative 1, we have plus x squared minus 7x plus 6. And combining like terms, we have negative x cubed plus 8x squared minus 13x plus 6, which means the volume V equals 2 pi times the integral from 1 to 6 of negative x cubed plus 8x squared minus 13x plus 6. The next step is to find the antiderivative, which is negative x to the fourth divided by 4, or negative 1/4 x to the fourth, plus 8 times x cubed divided by 3, or 8/3 x cubed, minus 13 times x squared divided by 2, or minus 13/2 x squared, plus 6x. And now we need to determine 2 pi times the difference of big F of 6 minus big F of 1. I've already done the simplifying here. We have 2 pi times the difference of 54 and 23/12, which simplifies to 625 divided by 6 pi. And this is volume, and therefore we can label the units cubic units. I hope you found this helpful.